Hi, now we are going to discuss neighboring group participation. Participation. It is also called NGP, neighboring group participation. To understand neighboring group participation, you must have knowledge about SN1 and SN2 reaction. I will brush it up in between during the discussion of neighboring group participation. Now, there are certain substrates where internal nucleophile is present. I'll represent that kind of substrate by using this general structure. So when the substrate having internal nucleophile, so this is internal nucleophile, and this is what LG means, living group. When such substrate undergoes nucleophilic substitution reaction in presence of external nucleophile, so this is external nucleophile we added there. This reaction follows different path. This reaction gives a product, a substituted product like this, and here I attach nucleophile. This kind of substituted product is obtained during this reaction, living group. But this reaction is somehow different than the SN1 and SN2 reactions. You know, in terms of its kinetics and stereochemistry. That means this substrate is not exactly SN1 or SN2. In terms of kinetics means rate and the stereochemistry. So in that connection you must know something about SN1 and SN2. First of all, I will clear that the rate of such reactions when we perform by using this kind of substrate is very high. That means rate higher than SN1 and SN2 reaction. And when we talk about stereochemistry, in SN1 reaction, you know, there is racemic mixture. Racemic mixture is formed, that is also called racemization. And in SN2 reaction, there is 100% inversion in configuration. Inversion. That means if the starting material is D, that will give L, and if starting material is L, that will give D. So this kind of stereochemistry we observe in case of SN1 and SN2 reaction. But here, when this kind of substrate is present and it undergoes nucleophilic substitution reaction, it gives 100% retention in configuration. So that configuration is retained. D is converted to D product and L is converted to L product. That means this is different than SN1 and SN2 reaction. Now we have to discuss this into more detail. So what difference is there? Actually, this kind of substrate when undergoes nucleophilic substitution reaction, it follows two steps. That step I am going to write here. So before that, I'll remove this part from the board. Okay, now we have, again I write that substrate, internal nucleophile and living group. So this is our step 1, you can say. So what happened here? This internal nucleophile actually acting as a providing a pair of electron from backside. So this is again SN2 attack. So by providing this pair, this leaving group is now removed and we get here cyclic intermediate. So we get here cyclic intermediate. Sometimes positive charge develops, or if it is charged, if it is negatively charged, it becomes neutral. So that is either positive or neutral depending on the structure of the starting material. Now this is first step. First step is exactly SN2 attack. It is a backside attack. Leaving group is going away. And we get here cyclic intermediate. We get here cyclic intermediate. Now, in second step, what happened? You watch carefully. That cyclic intermediate now may or may not be positive. Now, external nucleophile is attacking here or here. In this case, both carbons are identical, so I will not differentiate. I will not use both attack. But you have to consider both attack, either here or here. So you will get two products. So it is again another SN2 attack by the external nucleophile. So if it is attacking here, this bond will go back to the internal nucleophile as a as a lone pair of electron. So now we are getting this product, this substituted product. So this kind of mechanism, this kind of path is followed by the substrate when there is internal nucleophile. You can see here there are two SN2 attack. SN2 attack means inversion in configuration and again inversion in configuration. So two inversion means retention in configuration. That's why we can justify why there is 100% retention in configuration, because there are two attacks. Secondly, when we discuss is kinetics. So when we discuss is kinetic, the rate is very high. Rate is very high, abnormally. So that rate is abnormal. Rate is very high. Why? Because this internal nucleophile is very close, so it can attack to this carbon where the leaving group is present very fastly. So because of that, rate is very high. And one more term is used because of its very high rate, that is also called anchimeric assistance. Anchimeric assistance. So this is also, because of high rate, this is also called anchimeric assistance, and this is also called synergetic acceleration. Synergetic acceleration. So you just remember two terms, anchimeric assistance. And why it is called NGP? I'm coming back to the neighboring group participation because of this neighbor. So actually the whole mechanism is not NGP. The first step is NGP, neighboring group participation, because this neighbor is participating in this reaction. So because of this, that NGP term is given, and because of high rate, it is also called anchimeric assistance or synergetic acceleration. So you have to remember both terms, anchimeric assistance as well as synergetic acceleration. And when we talk about stereochemistry, so there is 100% retention in configuration. Retention in configuration. So you have to remember retention in configuration because of two SN2 attacks. One is internal and one is external SN2 attack. Now I'll provide here one example. So when I take this kind of substrate, for example, double bond O and OH, suppose CS3, EH and Br. This acid is taken. Now when this is treated with AgOH, and this is treated with AgO. First of all, there will be acid-base reaction because this is acid and this is base. So, and this is ionizing in the form Ag plus and OH minus. So that OH minus is actually removing this EH. I'll write here two lone pairs, and this is converted to the, I'll write here negative charge, double bond, two lone pair, and CH3 EH and Br. Now once this is produced and we get here Ag plus and H2O because of OH and EH. Now once this is generated, now negatively charged internal nucleophile is more nucleophilic as compared with this one. Now it will follow our NGP path by just doing backside attack, remove this leaving group Br, and we'll get here a cyclic intermediate. Now there is no negative charge. You can find out its formal charge because one lone pair is used. So this is internal intermediate, cyclic intermediate form. Now we have this nucleophile. This nucleophile is now ready for the attack. So it will attack here at this carbon. When this is, so if this will attack here, this double bond will open and it will convert back, and again it will expel out that OH. Nothing will happen, or otherwise this product will form. So it is going to attack here and we have to break this bond as a lone pair, and it is converted to the lone pair. So we are getting here this kind of stuff, that CH3, EH and OH. So this is our final product. When we add acid in the last step, that OH will be restored. So you know that very well. So what I am doing is actually I am just replacing this leaving group with the external nucleophile. But this, since there is an internal nucleophile, this will follow this kind of path. 2SN2 attack, 2SN2 attack, and if you remember here, this is a chiral carbon. So the stereochemistry of this chiral carbon is retained. So OH is taking exactly the position of Br exactly here. That's why there is retention in configuration. There is retention in configuration. Thank you so much.